Okay, so let's take a look at Theorem 17. So it says, if the limit b goes to infinity of the kth derivative of b times e to the minus sb is 0 for k less than or equal to n, then the Laplace transform of the nth derivative of f is equal to the s to the n Laplace transform of f minus s to the n minus 1 f of 0 minus s to the n minus 2 f prime of 0 dot 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 all the way down to minus the n minus 1 derivative evaluated at 0. Okay, so let's take a look at the proof for this. So proof. Okay, so we're going to prove the result using induction because we're trying to show it's true for all n here. Okay, so when you're proving by induction, you first prove the n equals 1 case. So when n is 1, then you'd have the Laplace of the first derivative. So by definition of Laplace, it'll be integral 0 to infinity e to the minus st times f prime of t. Now, we're going to use integration by parts to rewrite this. So let me write the integration by parts formula down here. Okay, so here's the integration by parts formula. So I'm going to let my dv correspond to f prime dt and my u correspond to e to the negative st. Okay, so my u is going to be e to the minus st, which I have here. So then du dt, derivative with respect to t, well, the derivative of e is itself times the derivative of the negative st with respect to t, which would be negative s. Therefore, it'd be negative s e to the minus st. And my dv is f prime dt. So therefore, if you integrate both sides, you'd have then v integral of f prime is just f. Okay, now let's plug it up here. So doing that, we have okay, so let me just mention down here, the du then would have been negative s e to the minus st dt. Okay, so this integral over here has limits on it, 0 to infinity, so it's improper actually because it has infinity up here. Okay, so anyway, so over here then you need to plug in these limits, so this integral should have 0 to infinity on it. And this will have limit b goes to infinity evaluated at 0 and b here, which I've done here. Okay, and so my f is the v times u is e to the minus st, which I have over here. Then minus integral v du. Du is the negative s e to the minus st, which I have here, times my v f of t, and my dt is here also. Okay, so let me erase a few things and we'll keep going here. Actually, these two minuses will cancel, become plus. I can pull the s out because the integral is with respect to t. So let me erase the bottom and we'll keep going. Okay, so simplifying a bit here, then we have limit b goes to infinity of, should be b on this, here and here. And then subtract, putting in 0 in place of t, so it'll be f of 0 e to the 0. That takes care of this limit part. And then, as I mentioned, the minus and minus cancel, and I can pull the s out. Okay, then you should realize then actually this guy here is the definition of Laplace transform of f. So we can write this as L of f here. And by our assumption up here, we're assuming that this limit is 0. That means that this is 0 because that's a special case of this guy up here. Okay, so this is 0. This is the Laplace transform of f, so let's note that. Okay, so again, this is 0, again, because we're assuming that this is true up here for all our k. So in particular, when k is 0, it's just going to be f here. So this will be 0. E to the 0 is 1, and this by definition is the Laplace of f of t. Okay, so let's simplify what we have then. Okay, so I wrote this guy first, going to be s times Laplace of f, then minus r, just be f of 0 here. And I claim this proves that n equals 1 case, because this is what we're trying to show up here. So if you put 1 in place of n here, you'd have the first derivative. Then you just have an s here, Laplace of f, which you have. Then it'll be 1 minus 1 would be 0. It'll be f of the 0 should be 1, just be minus f of 0, which we have here. Okay, so we've proven the n equals 1 case. Okay, now let me erase a few things and we'll continue. Okay, so now we'll do the induction step. So we're going to suppose that the result is true for the n minus 1 case. This implies then the Laplace transform of the n minus 1 derivative equals s to the n, Laplace transform of f minus s to the n minus 1 f of 0 minus s to the n minus 1 f prime of 0 dot 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 all the way down to the n minus 1 derivative evaluated at 0. Okay. So we need then to prove that the n case will follow from this one being true up here. So suppose this is true, we're going to show we can get the next case up being true also, based on this one being true. And that would set up like the chain reaction, or the domino effect if you want, because we've shown the n equals 1 case is true. So if we can show this induction step, that means that 2 is true. And if 2 is true, that means 3 is true. And then if 3 is true, that means 4 is true, case 4. And you set up this chain reaction that will not stop if you can show this induction step. Okay, so let's start. Okay, so here's by definition the Laplace transform of the nth derivative. So it's 0 to infinity e to the minus st and derivative dt. So we have to somehow use this result over here. So we're going to use integration of parts like we did on the n equals 1 case. So here's my integration of parts. I've adjusted it for to put the limits on it here. So it'd be integration of parts here. When you have 0 to infinity, it'd be 0 to infinity here. Then be uv, limit b goes to infinity, 0 to b, and then 0 to infinity v du. My u here I'm going to choose as e to the minus st again, just like the n equals 1 case. And my dv I'm going to choose to be this guy here. I'm going to write it over here. Okay, so my u is e to the minus st, so du dt will be minus s e to the minus st, so solving for du will be minus s e to the minus st dt. And my dv then would be f, nth derivative of f dt. So integrating both sides, you'd have v then equals, so now the integral of the nth derivative, well, for example, if you had the integral of the second derivative would be the first derivative, integral of the third derivative would be the second derivative. So in general, the integral of the nth derivative will be the n minus 1 derivative. So you'd have this then. All right, let's plug in up here then. So doing that, we get, all right, so plugging in, we get this then, because we have our uv, which is here, our u, e to the minus st, and our v, n minus 1 derivative. To be limit b goes to infinity, 0 to b here, then minus integral 0 to infinity, my v, which is the n minus 1 derivative, which I have here, times my du, which is negative s e to the minus st dt, which I have here. Here the two minus signs will cancel, and I can pull the s out over here. So let me erase some things below, and we'll keep going. Okay, so simplifying then, it'll be limit b goes to infinity, putting b in place of t, then subtracting, putting 0 in place of t, which I've done here, pull the s out, then by our assumption at the beginning of the theorem, we're assuming that this was 0, things of this form. So that's 0, that's 1, and that actually is the Laplace transform of the n minus 1 derivative. So let me note that here. Okay, note that here. And we're just about done now, because now we can use our assumption up here that the Laplace transform of n minus 1 derivative is this guy. So I can put that here, because that's the n minus 1 derivative, this guy. We're multiplying it by s. So multiply by s, we'll just add 1 to all the powers. And then you'd still have minus f minus 1 of 0. This should be of 0 actually here. Of 0. And that would be pretty much what we're trying to show. So let me just write that here then. Okay, so we're making this substitution in place of this guy then, because it's equal to, by our induction step, equal to this. So I put that here, multiplying it by s in front, we will have negative n minus 1 derivative evaluated at 0. So you multiply this s in then, we just add 1 to all the exponents, and I can put this at the very end, and then that's what we're trying to show. Let me just note that here. Okay, so again, multiplying this s in here, you'd have s to the n, the Laplace transform of ft here. Then you'd have s to the n minus 1, f of 0. And then this one then over here would be, at the end would be s, n minus 1, n minus 2 derivative evaluated 0. Then this guy here, you can put at the very end. And that's what we're trying to show. So hence, claim follows by induction. So we're done. Okay, so let's leave it there. We'll look at some examples using this in the next video.